Okay, then I guess our last topic is continuous functions on metric spaces, and what we're really thinking about here is we have a function, okay, that it takes in some object from a metric space as an input, and now it can spit out some object from a different metric space as its output, where we're used to thinking of functions spitting out real numbers or possibly vectors in Rn, but of course functions could spit out whatever. So we're going to wrap up talking about that whatever, and then again, for application, the whatever might be that our function spits out a function, for example, a continuous function, and application begin proving existence of solutions to differential equations, integral equations, things like this. So this is 8.3, continuous functions on metric spaces. Okay, so again, we're going to suppose now that we have two metric spaces. They could be the same or they could be different. So A and rho is a metric space. A is a collection of objects, rho is a metric. And then B sigma is another one. Okay, and now we're going to consider functions of this form that take elements from A and spit out elements in B. Okay, so I mean, there's many different examples of this that we could think of. You know, maybe A is a set of people in some room, and we put a metric on it. Maybe rho is the discrete metric, for example. Okay, and maybe, for example, B is the set of points on the sphere that we might, so you're on Earth somewhere, which is basically a sphere, so we figure out your latitude and longitude and locate you that way. So B maybe is points on the sphere. And maybe sigma is the geodesic distance on the sphere. Okay, now most of the things that we need for calculus stay the same. You know how to define these things, right? We have the domain, right? It's just the things that we're allowed to stick in F. So domain of F is just the set of things that we're allowed to stick in the function F. So all the things in our input space such that F of u is defined. And then the range is just all the possible output values. Okay, so again, these are all the possible values that live in our output space now that we can somehow reach. So such that f of u equals v for some u. Okay, we can write down the definition of the limit. You already know how to write down the definition of the limit. We've written it down plenty of times. We just need to write everything in the language of metrics now instead of subtraction. Okay, so the limit okay, so the limit is equal to L if, and now usual definition. So for every epsilon greater than 0, there exists some delta greater than 0 such that, well, if u is in the domain of f, and okay, now we want the distance between u and u naught to be less than delta. So the distance between our inputs are measured in one metric. Okay, so right, as usual for limits, we don't care what happens when u equals u naught, we care what happens close by. So we have a strictly less than there that matters. And if this is true, then we expect f of u and L to be within a distance epsilon of each other. Well, now f of u is not a real number anymore, necessarily. So I can't just write f of u minus L. That might not make any sense. Now I have to compare them in the appropriate metric. So f, I'll put something in B. So this is my appropriate metric. So the distance between f of u and L can be made less than epsilon. Right, and again, the problems are the same. You just have to write things in the language of metrics. So we'll just do a quick, easy one. So let's suppose that f takes the space of complex numbers with some metric, which I'll tell you in a second, to the space of reals. Okay, so it is a real valued function. What we're just going to worry about is making sure we write this all in the language of metric. Okay, and what is rho? Rho is going to be, so the distance between y and z is going to be the usual, all right, we compare the real parts and we compare the imaginary parts. And sigma can be our usual Euclidean metric. Okay, so let's take a function. Where's my function? F of z, say it just gives us the real part of z. And we want to show that the limit as z approaches 3 plus I of f is equal to 3. Okay, so it's a straightforward problem. We're not trying to do any crazy magic here. We just want to make sure we can write the solution out, again, using the appropriate language of metric. So what do? We pick an epsilon. Okay, now we need to look at all complex numbers that are close to 3 plus I. So we look at all these complex numbers such that they're within some distance delta of 3 plus I. Okay, so let's write what that means. That certainly means that, well, here's our metric. So this certainly means that, well, the real part of z minus the real part of 3 plus I, that's 3, plus the imaginary part of z minus the imaginary part of 3 plus I, that's 1. Is going to be less than delta squared. And that means, in particular, this part is certainly less than delta squared, and this part is certainly less than delta squared. So the real part of z minus 3 is at most delta, and the imaginary part of z minus 1 is at most delta. Okay, now what do we need to do? We need to look at the distance between f of z and our candidate limit, which we think is 3. Okay, so this is the part where normally you would write f of x minus L and manipulate. Now instead of that, we're going to write the metric between f of z and 3. Okay, that's just a standard Euclidean metric. All right, what did we say f was? F is the real part of z. Which is known to us to be less than our delta. So we can force this certainly to be less than epsilon, right? As always, we simplify. We write down the metric that we need, put in all the definitions, simplify, force it to be less than epsilon, and this is certainly true as long as delta is less than epsilon. So we say, great, this limit was indeed equal to 3. Okay, so limits are okay. Right? It's the same definition. You take this usual definition in your head and you replace things that don't make sense with the metric. All right, and similarly we have continuity. Right? F is continuous. We've got different ways of characterizing continuity. Okay, so F is continuous at some point. We'll write the epsilon delta definition, but then we know in the past there were equivalent ways of characterizing continuity, and all of that still holds. There's really no difference to the proof that they still hold. So if for every epsilon greater than 0, there exists a delta greater than 0, right, such that, okay, it's our limit definition, but now the limit L is replaced by f of u naught. Okay, so such that if u is in the domain and u is close to u naught within the distance delta, right? Now, again, the important part is now this is the language of metrics. Okay, then we're going to have the same thing almost that we had in the definition of the limit, right? But now our limit is the actual function value. So now the distance between f of u and f of u naught is less than epsilon. All right, so again, there's nothing new or different here. And we've seen in the past there are different ways to characterize continuity. One is the obvious one, that the limit is equal to the function value. That still works, okay, because limits still make sense. So the limit as u goes to u naught of f of u equals f of u naught. And then the other characterization we had in the past was in terms of sequences. And working with sequences, I mean, it tends to be useful for a lot of the things we want to prove. This is obvious and intuitive, but working with sequences makes it easier for us to bring in tools like completeness, compactness, things like that as we're trying to argue things. Okay, so this was for all sequences that converge to u naught. It says if the sequence converges to u naught, then if we take the function and apply it to the sequence, the function values will also converge to the function value that we want. So then the limit as n goes to infinity of f of un equals f of u naught. This is a theorem, yeah. It's a theorem that we've proved maybe last semester. Not in the context of metric spaces, of course, in the context of real valued functions. But nothing changes. I mean, you can see, I think, nothing really changes for most of these foundations as we move from real valued functions to functions on metric spaces to metric valued functions. Right? We just have to rewrite the theorem explicitly putting the metrics in. Okay, it's also true that a continuous function, we like continuous functions, defined on a nice set, whatever that means, preserves the property of it being a nice set. And we've made arguments like that before, especially in the context of vector value transformations, and we cared about this a lot when we did change of variables theorem. But in particular, continuous functions preserve compactness, which is great. We like compactness because compactness lets us talk about convergence of sequences. Okay, so our first key result here is that if f is continuous on a compact set, then the image of this set is also a compact set. All right, so start with T. T is compact. I mean, our intuition is compact means closed and bounded, which we know is not true necessarily, but I'm going to draw it that way for ease of drawing. Okay, then it means that this image set is also compact. But again, maybe we're working on the space of continuous functions from A to B, and this maps. And we have a function that takes a function that spits out a new continuous function. Well, this is if we started with a compact set, right? So we've got uniform boundedness, we've got equicontinuity. We pass it through some weird function, maybe it's some kind of integral operator or whatever. This will preserve the uniform boundedness. It will preserve uniform continuity. So whatever it spits out still has those nice properties that we want to play with. And the good news is we have the tools in place to make it pretty easy to work with compactness at this point. It wasn't easy to get those tools. We worked hard for them, but now we can use them with a great ease. So one thing that we know about compactness, we've defined it in terms of this Heine-Borel characterization. It's equivalent to saying every sequence has a convergent subsequence. Okay, so if I want to prove something is compact, I don't have to prove Heine-Borel. I could just take a generic sequence and show it has a convergent subsequence. And that can be a lot easier. Again, I said here, working with sequences is often a lot easier. It may or may not be the most intuitive. It might be more intuitive than Heine-Borel, I don't know. But it's often easier. So I'll throw this out there. If you're asked to prove something is compact, this is maybe where I'd start if I didn't have a good reason to do something else. So I'm going to, okay, I know this set is compact. I'm going to take any sequence in this set and try to show it has a convergent subsequence. Okay, so let's let Vn be any sequence in my image set. And our goal is going to be to show that there is a convergent subsequence. Okay, with, of course, by convergent I mean there's a limit and the limit stays in this image set. Okay, so, well, let's start. Vn is in this set. So what does that tell us? What does it mean for something to be in the image set? Yeah, if it came from somewhere. So if this is Vn right here, it had to come from somewhere. So there exists some Un in T such that Vn equals f of Un. Okay, so I started with a sequence over here. This is the sequence I care about. This is the sequence I want to prove something about. But corresponding to the sequence, there's another sequence that lives over here. Now, what do I know about the sequence over here? It has a subsequence that converges, right? So over here, this set I already know to be compact. So that means this guy certainly has a convergent subsequence. So T is compact. Implies there exists a subsequence UNK, and there exists some U not in T, such that this subsequence converges. Now I want to use the fact that I have a convergent subsequence over here to now say, well, the corresponding subsequence over here must also converge. Well, I haven't used the fact that f is continuous yet. That's probably important. F is continuous, so we can start looking at epsilons and deltas. The limit, okay, we can maybe say something about the limit. So let's see what that says about the limit. I don't quite have this yet. I do have something about sequences here, sequence characterization. Again, this is useful. So we know since f is continuous that if I have this sequence that converges to U naught, then the function values should converge to f of U naught. Okay, so the limit of f of UNK equals f of U naught. Well, these f of UNK, they're not some new objects that have just popped up at this moment. They, of course, correspond to a subsequence of this original sequence that we took, right? So this is exactly equivalent to saying that the limit of this VNK is equal to f of U naught. So we've got a subsequence that converges to something. Does this live in the image set? For sure. U naught lives in T. So this certainly lives in the image set. And that's it. We found a convergent subsequence. So, I don't want you to get terrified and intimidated by this idea of compactness and showing something as compactness. It was a lot of work building up the machinery, but we have the machinery now, and it's relatively straightforward to use in most cases, right? We have simpler, we start with the general definitions, move from there to what are easier ways to characterize. And this is a relatively simple way to characterize compactness. And it's a nice way to characterize compactness because it gets at what we're actually interested in a lot of cases. So this is enough to say, indeed, f of t is compact. Right, and this is a perfectly reasonable result or exercise. I think, any of you can sit down for a little bit, work through the definitions, and I didn't do any magic here. I just worked through the definitions in a pretty straightforward way. It's also true that if f is continuous on a compact set, then it is uniformly continuous. Okay, and what is uniform continuous? How is that different from normal continuity? Do you remember? Yes, exactly. That's exactly it. The tolerance, this delta, stays the same. So our usual definition of continuity says, well, like, let's check continuity at U naught. All right, given a U naught, given an epsilon, I can find a delta. Uniform continuity says, I don't care which U naught you give me, right? Anywhere on this set, you give me an epsilon, I give you delta, and you can use that delta anywhere on this set. That's uniform continuity. Okay, so F is uniformly continuous on a set T, F. For every epsilon greater than 0, there exists a delta greater than 0. Okay? Such that if we take any 2 points on this set and compare them, so if the distance between these 2 points is less than delta, then the distance between the function values is going to be less than epsilon. And uniform continuity was, I guess, an important ingredient in equicontinuity, that we somehow just have a delta that just works everywhere. Right? Equicontinuity is more than that, because we also have a whole bunch of functions to choose from. But this is an important ingredient that we need when we're playing with compactness. Okay, so going back to the proof of the result. Well, let's suppose not. Well, what does that mean? That means this definition doesn't hold. And that means somehow I can find some epsilon such that I can just never force these function values to be less than that epsilon. Okay, so let's try to write down what this means. It means there exists some epsilon bigger than 0, such that, no matter how small delta gets, I can always manage to violate this condition. Okay, so I said I like doing things in terms of sequences. Let's get used to doing things in terms of sequences. I'm going to pick a sequence of deltas that gets smaller and smaller and smaller. So such that if delta n equals 1 over n, okay, we can always find some points, un and vn, okay, such that these points are close together. Okay, well, again, what are we saying? We're saying no matter how small delta is, no matter how small a delta you give me, I can find some points that are within delta of each other, but nevertheless violate this, such that this is true, and the distance between these function values is bigger than or equal to epsilon. Okay, so we're assuming that f is not uniformly continuous. That's the thing that we're trying to prove. That's over there. We know f is continuous. We know our domain is a compact set. Okay, so this set here, this is compact. So what do we know since this is compact? I can get convergent subsequences of these guys. So let me start with this one, just to pick one. Since T is compact, there exists some subsequence U and K and some limit in my set such that this subsequence limits to U naught. Okay, U naught, of course, being in T. Okay, so one of these guys has a convergent subsequence. Of course, we can get a convergent subsequence for this guy too, but we don't really have to do much more work to get there. So this guy is getting closer and closer to U naught. This guy is getting closer and closer to UN, right? So they're getting closer and closer together. That means the V and Ks are also going to converge to the same point. Okay, I said that in words, but I can write that out precisely. Okay, so the distance between V and K and U naught. Well, I'll do some triangle inequality. I compare V and K to U and K. We know that distance is small. Then we compare U and K to U naught. That distance is small. Yeah?
Is that a limit when K goes to infinity?
This is a limit as K goes to infinity. Yeah. All right, the distance between the UN and the Vn is less than 1 over n. Okay, and this is something that we can make as small as we like. We know that as K goes to infinity, this goes to 0, this goes to 0. Okay, so indeed, if I take the very same subsequence of these, I get actually the very same limit. Okay, so we've got these guys through a subsequence both converging to the same value. Now I can, I need to get to here, or I need to create a contradiction with this somehow. So we need to take the function values of these. Well, we have a continuous function. We're not uniformly continuous at this point, but it's continuous. So that means that if U and K converges, f of U and K converges. And similarly, f of V and K converges. So since f is continuous, right, the limit as K goes to infinity of f of U and K equals f of U naught. Right, that's one of our ways of characterizing continuity, that if I have a sequence like this, I can stick an f in front of both sides of these and it's still true. And I can do the same thing here. And that starts to suggest that we're going to get a contradiction with this point here, right? If this guy and this guy are both approaching the same value, then the distance between them should be going to 0, right? Eventually it will be less than this epsilon. Okay, so the distance between f of U and K and f of V and K right, I'll do my triangle inequality so that I can feed in these two facts. Okay, and again, we know that f of u and k converges to f of u naught. What that means, by definition, is that the distance between them can be made as small as I like. Similarly here, so this sum can certainly be made less than epsilon for large enough k. Okay, so this is a contradiction. And therefore our assumption was bad, and it must be actually f is automatically uniformly continuous. Questions? I hope this is not too bad today. I know that we've done a couple weeks of involving some big intense proofs. We've built up a lot of useful machinery, but now the machinery is there. Again, it's not that hard to use, right? You do a few problems and you start to see that we're really just playing with sequences in almost the same way every time. So keep the definitions close at hand. Again, there's different characterizations of a lot of these concepts of compactness, of continuity. Working with sequences is often the easiest. So I'll stress that again. If you have these kind of problems, my first attempt, barring other information, would be how can I make this a problem about sequences? Okay, so how can we use this? We want to solve some equations. We want to know that we can solve some equations. So a common approach is some sort of fixed point iteration. So this is what we're going to think about. How can we analyze fixed point iterations where, again, we're probably not having a function that goes from R to R. We're going from some other space, probably a space of functions. But we can still define fixed points and still use fixed point iterations. So let's define a fixed point, first of all. All right, so if we're talking about fixed points, that just means you have an input, you stick it in your function, it spits out exactly the same thing. So first of all, we're working on the same metric space as our input and output space, which later will be the space of continuous functions, for example. Okay, so we have a function that's defined on some metric space, and it spits out a value in the same metric space. Now let's define the concept of a contraction mapping. This is, which you might remember, contraction mappings are kind of one of the easiest ways to come up with to analyze fixed points. So what does a contraction mapping say? A contraction mapping is a function that takes 2 points and makes them closer together, and then makes them closer together again, closer together again. Okay, so if I want to define this, I'm going to say that there exists some quantity alpha between 0 and 1, such that, okay, I start with 2 points, say u and v, and they're some distance apart. Now I stick them both inside my function, and the results I get are closer together than before. So I'm going to say that the distance between f of u and f of v is less than or equal to alpha times the distance between u and v. So things got closer together. All right, this we call a contraction. So, very good question. You're thinking about things being Lipschitz, and yes. so there is definitely interpretation of this in terms of Lipschitz. So let's just actually think about this for a second. Think about if we were just dealing with the reals under our usual metrics. So for example, if A is the reals and rho is our normal distance, then what does this say? This says that the distance between f of u and f of v is less than or equal to alpha times u minus v. So yes, there's a Lipschitz constant right here. So what this is actually saying is that you have a Lipschitz constant that's less than 1. Or if f is differentiable, it says the derivative is less than 1, strictly less than 1 always. Okay, so let's stick with this example on the reals for a second. Let's say that f takes a closed interval and maps it somehow into a closed interval, and it's a contraction. Okay, so here's A to B on both axes. Now what I'm interested in a fixed point. A fixed point is where f of u is equal to u. Okay, so a fixed point means the function should lie somewhere on this line. This is the line y equals x, if this is my x-axis and my y-axis. If f has a fixed point, it will cross this line somewhere, right? So if my function is always over here, then no go. If it's always over here, then again, no go. But if it crosses the line, the point that it crosses the line, we're going to have that the input is exactly equal to the output, and that's our fixed point. Okay, so now what's the idea here? Well, either f of a equals a and we've started at a fixed point, or we start somewhere up here. Now, we have a function that is forced to stay in this box. Right? If it's forced to stay in this box, well, then what happens? It's going to have some value at f of a, and it's going to have some value at f of b. And if it's a continuous function, well, we think it's continuous. We think it's Lipschitz continuous, actually, right? If it was discontinuous, it could go here and then jump to here. But we think it maybe is probably continuous, just by virtue of being a contraction. And that means we've got a fixed point somewhere. And actually, if it's a contraction, in this example, the derivative or the Lipschitz constant are less than 1, there's going to be a unique fixed point in here. Because once we've crossed here, it's sitting here below the line y equals x, it can never turn around and jump up steeply enough to catch this line again, right? It would have to, this line has slope 1, so in order to catch back up with the line again, it would have to turn around and have a slope bigger than 1. So actually there's a unique fixed point. Okay, that's maybe relatively obvious for real valued functions of the reals, but this all still holds for contractions on a more general metric spaces. So I'll start by the observation that, which seems to be true on the reals, But it's, again, also true more generally, contraction mappings are continuous functions automatically. And, you know, you can almost read that off directly from the definition. Okay, so let's call this a lemma. If F is a contraction, then F is continuous. And again, it's almost written exactly there already. So we pick epsilon to be bigger than 0. And what do we need to look at? We need to look at the distance between f of u and f of v and try to force it to be less than epsilon. Well, this we know is less than or equal to the distance between u and v. And this we can certainly force to be less than epsilon as long as the distance between u and v is less than epsilon over alpha, and this becomes our delta. And that's continuity. So contractions are automatically continuous. And that means even in a more general metric space, this is still going to hold. You know, we start above the line y equals x, right? And we've got to cross it somewhere. We're going to stay in this same box. Okay, so f is continuous. Okay, so let's write down our big contraction mapping theorem, which is just this. And actually, the proof is not really different than how you would prove it in this case. You just have to use the language of metrics. So this is the contraction mapping theorem. Okay, so if f is a contraction, of a complete metric space, okay, then we can find a unique fixed point. That's a unique solution in A. Okay, the one condition I added here was completeness of the metric space. So one of our favorite metric spaces, aside from Rn, is the CAB, the continuous functions on A to B. That's a complete metric space. And by the way, that generalizes just fine to continuous functions on higher dimensional sets. So you don't just have to be on intervals, you can be the sets in Rn. So proof, there are two things to prove. The fixed point exists and that it's unique. I'll start with uniqueness. Uniqueness is usually easier. What's the standard approach to proving uniqueness? You suppose there are two solutions, and then you show they must be equal. Okay, so first we'll do uniqueness. Okay, so let's suppose that there's two of these guys. All right, I want to prove they're equal. All right, how do I prove they're equal? I prove that the distance between u and v is 0. So what I want is to look at the distance between u and v and hopefully show it's 0. well, I may as well bring in the fact that we've just made this assumption. So this is the same as the distance between f of u and f of v. And then I'd also better bring in the fact that we're working with a contraction. That obviously matters to this theorem. So we know this is less than or equal to alpha times the distance between u and v for some alpha. Okay, well, I've actually got the same thing almost on the left and right, so I'll rearrange a little bit. Well, I know that this quantity, alpha is between 0 and 1, but it's not equal to 1. That was important for uniqueness. And you can see from the picture that's important for uniqueness because my function could just be this line and everything be a fixed point. So it's certainly necessary for uniqueness. This guy we know to be positive. This guy we know to be bigger than or equal to 0 because it's a metric. So the only possibility here is that the metric is 0, which means u equals v. So fixed points are unique. And that's a typical uniqueness argument. Uniqueness arguments often don't have to be complicated. All right, existence. Existence is a little more work, but not too much. Again, it's not so different than just doing this on R. Changing the metric space doesn't really change things. It just means we have to use the language of metrics. So what I'm going to do is seek the fixed point through an iteration. I'm going to come up with a sequence that I hope converges to the fixed point. So let's set up a typical fixed point iteration. Let's choose a starting value. Okay, and we define a sequence. Okay, so to get the next value in my sequence, I plug my previous value into my function. Okay, so we want to argue two things. Well, one, that this is a sequence that converges to something, and two, that the something it converges to happens to be a fixed point, happens to satisfy f of u equals u. Okay, so that's our goal. Okay, so I need to start looking at the difference between things. I'm going to start by looking at the difference between neighboring things. I mean, ultimately, I want to show that this is a Cauchy sequence, right? Cauchy sequence is the general way I show something converges if I don't know what the limit is. So I want to show it's Cauchy. To start with, there's kind of an easy way to compare neighboring terms. Comparing neighboring terms doesn't give me Cauchy, but it's a start. It's what I've got to work with. So let's start by comparing neighboring terms. So this is the distance between, if I just put in how these are defined. And this we know, since we have a contraction, is bounded by alpha times the distance between un and un minus 1. Okay, so things got closer together, right? We started with our 0th and first values, whatever they were, and we iterate, well, things somehow got closer together. And the idea is, again, they should keep getting closer and closer together, and hopefully not closer together, but wandering through space, but hopefully closer together and converging to something. Right now, we just know they're getting closer together, but again, they could be wandering through space. Right? That's what happens when we look at partial sums of the harmonic series, for example. Yes, the terms get closer together, but they wander up to infinity. So this isn't good enough yet. We need to tighten this up. I could certainly carry this back another step. In fact, I could keep carrying it back n steps. And now this is just some number. Alpha to the n, which is pretty small. If n is big, this is pretty small. And this is just some number, and it doesn't depend on n anymore. It just depends on how I initialize. Okay, so this is a little better than just saying terms get closer together. It gives me a rate at which they get closer together. And I'm going to exploit this rate to show that I have a Cauchy sequence. Okay, so we want to show this is Cauchy, so let's pick two different values of n and m. And I'll just say that n is bigger, just to pick something. And we need to look at the distance between them. Okay, and in any case, well, I can compare the distance between neighboring terms. So I've got to put this in terms of distance between neighboring terms, which the triangle inequality certainly lets me do. And the distance between neighboring terms, right, I can bound really precisely. Right, so this is bounded by alpha to, I guess, the lower power. So alpha to the n minus 1 plus alpha to the n minus 2 up to alpha to the m, all times this same number, just this initial distance. What is this? What can I do with this? It's a geometric series, right? And we have, it's a finite geometric series. We have a formula for that, right? So this is exactly equal to alpha to the m, 1 minus alpha to the n minus m, divided by 1 minus alpha. Okay, I'm not dividing by 0 because alpha is strictly less than 1, so that's good. We know when we're trying to show something is a Cauchy sequence. At the end of the day, we don't really like having both n's and m's floating around. It's nice to get it in terms of 1 that's used to solve for our n star. So alpha we know to be a positive number, so I can certainly say that, well, this just made things smaller. Get rid of it. And that's probably as simplified as I'm going to get. So I say, all right, can I make this less than epsilon? Well, this just involves solving for m. And this is something I can do if both n and m are bigger than, all right, log of epsilon 1 minus alpha over the distance between u1 and u0 divided by the log of alpha. Okay, again, that's a perfectly well-defined quantity because everything in here is positive. As things get small, I guess, all right, this logarithm will give me a negative value, but this will also give me a negative value. So it's a positive number, and this becomes my n star. So we've just written down that actually we have a Cauchy sequence. And good news, we're working in a complete metric space, so Cauchy sequences automatically have limits. Okay, so since we assumed A is complete, right, that matters too. There exists some limit. Okay, so then our last question is, what is the limit, right? Our goal was not just to show that this fixed point iteration converges to something. We want to show the existence of a fixed point. So I've identified this object, whatever it is, that's the limit of the sequence. Now I need to show that f of u naught equals u naught. Okay, so let's see what it is. Well, f of u naught, well, that is equal to the limit of f of un, because f is continuous, right? Contractions are continuous. Here's where it matters. I need to get this in terms of not f's, but in terms of u's. There's a relationship between them, though. The u's were defined in terms of the previous f. So this object, if I use my recursion formula, this is exactly how I defined un plus 1. And we know this is a sequence that converges to u naught. So we've identified some point in our metric space that has the property that f of u naught equals u naught, and that's our fixed point. Questions? This proof may look familiar to some of you. If you've seen a fixed point proof before in the context of real valued functions, but this is really what the proof looked like. I mean, the only difference is that it would have just said u1 minus u naught here. That's the only difference. There's really no new machinery that we need for this. Once we have the big concepts of completeness, compactness, they're powerful tools that let us do a lot of things. Yeah? Since A is complete, but this word is not complete, thank you. Okay, so let's do an example. Let's show the existence of a solution to an integral equation. Which sounds like a big ask, but actually this machinery is powerful and it will not be hard to apply it to be able to use it here. So let me give you the integral equation. And I'll give you some of the conditions on parameters, which will not be obvious now why they're needed, but when we do the proof, they'll pop right out for free. So let's suppose that we have a function which is continuous. Okay, so we have a function of one value that's continuous. We also have a function of two variables. That's continuous. Okay, and of course bounded. Okay, a continuous function on a compact set is of course bounded. I'm going to give you the explicit value of the bound here because this matters. Now we're going to also have some parameter, lambda, that is not too big. This is how big it's allowed to be at most. And we want to show that there exists a unique continuous function that satisfies this integral equation. U is equal to h plus lambda times the integral from a to b of k of xy, that's kernel, times u of y dy. Okay, this looks, at first blush like an intimidating problem. Where do we start? It's fine. That's, as a mathematician, that's a normal feeling. So let's not get overwhelmed. Let's think about the tools we have here. One of the tools we have, which is very popular for existence of solutions, is fixed points. There's a lot of different fixed point theorems. This is one of the simpler ones to write down and work with. So we want to write this as a fixed point problem. We've got an obvious metric space to work with. We're looking for solutions that are continuous on this domain. Okay, so I'm going to start by defining a function that I want to find a fixed point of. Okay, so we need a function. Okay, and we want it to be a function between a metric space and the same metric space. All right. This, of course, is a complete metric space, we know, which is good. That means that we'll be allowed to use our fixed point theorem. All right, now let's try to define this function in such a way. So remember, this function takes in a function and it spits out a new function. And we want it to be such that fixed points satisfy this equation. So what I'm going to do, what I want is u equals f of u. So I'm going to somehow have my f of u be everything on the right-hand side. Now, again, this is not just at a particular value of x. It has to be a function. So let's let f of u equal v. Okay, so this is how I'm defining f of u. F of u is defined as v, where v is the function such that for all x in my domain, v of x equals precisely this. Okay, so again, v is a function of u, right? You give me a different continuous function, I spit out a different new continuous function. And this is still a continuous function, okay? I started with h being continuous, everything in here is continuous. This is going to preserve continuity. Okay, so indeed, v is still a continuous function. That's not a problem. Now, what we really want to know is, if that matters that we land in the same metric space, but what we really want to know is this a contraction? Because if it's a contraction, then we're done. Then we have this lovely fixed point theorem that tells us, yeah, sure, there's a fixed point. So this is our big question. Is f a contraction? So what do I need to do? I need to pick two things in my space and show that f makes them closer together. Any two things. Okay, so let's let u1 and u2 just be any objects in our metric space. Now to these functions, we have new functions that we define, v1 and v2. Okay, so f of u1 is v1, f of u2 is v2. Okay, and now we need to compare them in our appropriate metric. Okay, so I need to look at, well, v1 of x and v2 of x. I need to compare them, and I need to find the maximum difference between them over all x. Okay, so let's start with a fixed x, and then we worry about taking the maximum. What I need to look at is the distance between them. And we hope that the distance between them is somehow less than the distance between u1 and u2. That's what it means to be a contraction. Okay, so, well, v1 equals h of x plus stuff, v2 equals h of x plus stuff. So when I subtract, h minus h goes away. It doesn't matter what h is. Okay, then I'm going to have lambda times this integral with a u1 minus lambda times this integral with a u2. Okay, so this is really just lambda times this integral involving u1 minus the integral involving u2. All right, and now we start bounding things. Okay, we know that this is bounded by what happens if we keep the absolute value sign inside. It's a property of integrals. We know that k is bounded by m. And we know that u1 minus u2, right? I mean, this integral is hopping all through space, all through AB. But this is going to be bounded by the norm of u1 minus u2, right? The metric between u1 and u2. So all of this is less than or equal to lambda times the integral from a to b of m times the maximal possible distance between u1 and u2. I had a condition on lambda. Now you'll see where it matters that if we start ramping up this parameter too much in our integral equation, things might go haywire and may not work. But this lambda we know to be less than 1 over m times b minus a. All right, this is the integral of a constant at this point. So that's m, the norm of u1 minus u2 times b minus a. Okay, and indeed, this is strictly less than u1 minus u2. Okay, this is strictly less than u1 minus u2 for all x on a compact set. That means the maximum is attained. The maximum is also strictly less than u1 minus u2. Right, and whatever this ratio is, you can use to define your alpha that is strictly less than 1. So indeed, what did we show? We showed that we have a contraction, right? This is f of u1, and this is f of u2. Let me write it explicitly in terms of the metric, actually. And it is going to be less than or equal to alpha times the distance between u1 and u2 for some alpha that is strictly less than 1. not equal to 1. There's some value that's strictly less than 1. And that means we have a contraction. Well, if we have a contraction, we already know we're playing on a complete metric space. We've got a fixed point. And a fixed point, okay, if this was our f of u equals u means we've got a solution to our integral equation. Okay, so f is a contraction. All right, CAB is complete. And that means we know there exists a unique fixed point. And we set the problem up so being a fixed point is equivalent to being a solution to the integral equation. So, I mean, an intimidating looking problem at first blush. It's really not hard to solve, right? If I gave you this problem and I said, prove this using the fixed point theorem, there wasn't much that we had to do here. These are standard types of estimates that we've been doing all year long. So I guess this is the takeaway that, we've built up some complicated machinery and it was hard. We worked hard and suffered through it a little bit. It lets us do a lot though. It's powerful machinery and we can start to prove some pretty sophisticated results without too much work.